So we're now going to consider a special class of dielectrics known as linear dielectrics, and we'll be looking at the definitions of susceptibility, permittivity, and dielectric constants. So at the very start of this topic, we were talking about what caused polarization. And polarization happened when we had some dielectric, which was put into some external electric field. So let's call this external electric field E0. And the dipoles within our dielectric could spin around and align themselves a little bit with the field, or we got an induced polarization within the molecules making up this dielectric. So we ended up having a polarization which slightly aligned with the electric field, and this generates its own electric field. So an equation we can write down to relate the polarization and the electric field is that P is equal to epsilon naught times this susceptibility, which is the Greek letter chi with a little subscript E, times the electric field. And this is not for all dielectrics. This is just for the class of linear dielectrics. So this here is our susceptibility. And it's a dimensionless constant. Dimensionless. And that comes about because we've got the epsilon naught here. So the epsilon naught is included to ensure that this susceptibility is a dimensionless constant. Now, it's really important to note that this electric field here is not this applied electric field here. It's the electric field which is applied as well as the electric field generated by the polarization of the dielectric. So this can make this a little bit hard to deal with because we've got a feedback loop here when we have an applied electric field that generates a polarization which adds to the applied or at least changes the applied electric field. And so it turns out that it can actually be a bit simpler to work with the electric displacement rather than the polarization here. And so using our equation for electric displacement, we've got that the electric displacement is equal to epsilon naught E plus P. And so this is epsilon naught E plus epsilon naught times the susceptibility times E. And we can write this as epsilon naught times 1 plus the susceptibility times the electric field. Sorry, I've written that wrong. And so we can write this as the electric displacement is equal to some other constant, which we'll call epsilon, which we'll refer to as the permittivity times the electric field, where epsilon, the permittivity, is equivalent to epsilon naught times 1 plus the susceptibility. So if you know the susceptibility, then you know the permittivity. These are very, very closely related to each other. Another constant that is sometimes used is what's known as the relative permittivity, which is equal to epsilon divided by epsilon naught, which is just 1 plus the susceptibility. And this is also referred to as the dielectric constant. So occasionally you'll see that written as K or kappa. So this is the relative permittivity or dielectric constant. And this is the permittivity. Sorry about all the new words and Greek letters that we're using to describe these things. So to give you an idea of the size of these dielectric constants, I mean, you can look them up, but for a vacuum, we've got the permittivity of free space is just epsilon naught. And so in that case, kappa is 1. So for a vacuum, we've got kappa is equal to 1. For diamond, we've got a dielectric constant of 5.7. For water, it's 80.0. For most gases, it's 1 point something small. So for helium, for example, helium, it's 1.000065. So for like atomic gases, it tends to be very close to what it is in a vacuum. Now, one of the ways that this can be somewhat useful is it does give us a way to relate the bound charges to the free charges. So let's look at how we can go about doing that. We've got that bound charges are given by minus the divergence of the polarization. We've seen that before, and I've written it down up there. We're just using this. And now what we're going to do is we're going to replace this polarization with the displacement minus this electric field term. So this is equal to minus D minus epsilon naught E. And then using this term here, we can write that E is equal to D over epsilon, which is the permittivity. So this is equal to D over epsilon naught times 1 plus the susceptibility. And so we're going to substitute that in here. So this is equal to minus the divergence of D minus epsilon naught D over epsilon naught 1 plus the susceptibility. And now you can see these epsilon naughts will cancel out. And what I can do is pull my displacement out the front. So this is equal to minus the divergence of the displacement times 1 minus 1 over 1 plus the susceptibility. And then remembering Gauss's law for displacements, Gauss's law for displacements told us that this thing here was equal to the free charge density. So this is minus rho f, and then inside the brackets we can write this at all over 1 plus chi e. We've got 1 plus the susceptibility minus 1. And so this is equal to minus the free charge density over the susceptibility over 1 plus the susceptibility. So this is a nice way to relate this bound charge density to the free charge density. Doesn't work near the surfaces because there the susceptibility isn't like well defined. But it's a nice equation to use inside a dielectric. Okay, so let's put this into use. So in this example, we've got a metal sphere of radius A, which carries a charge Q. It's surrounded out to radius B by a linear dielectric material of permittivity epsilon. Find the potential at the center relative to infinity, and then hence find the polarization, the volume bound charge density, and the surface charge density, bound charge density, on the inner and outer surfaces of the dielectric. Okay, so let's start by sketching a diagram, and then we'll work through what we need to work through. So here is our metal sphere with radius A, and then it's surrounded by a dielectric here at radius B, and we're asked to find the potential of the center relative to infinity. So we want to find the potential here, and in order to do that, what we imagine doing, like normal, is bringing a charge in from r equals infinity all the way down to the center here. And we know that the voltage is equal to the integral of the electric field over the path. Well, with a negative, I left off the negative. So what we'll need to do is work out what we can about the electric fields in each of these regions here, and use that to calculate the total potential. Now, some of these regions, it's relatively easy to work out the field for. We know that this is a metal sphere, so it's a conductor. And so we know that the electric field inside the sphere is equal to 0. Now, the dielectric isn't charged, but it does have bound charges, which is going to give it a polarization, but that is not going to affect the electric field out here. So the electric field out here is just due to the enclosed charge. We know that from Gauss's law. We've seen that lots of times. So hopefully by this stage, you know that the electric field out in this region is going to be given by 1 over 4 pi epsilon naught times Q over r squared, and that's in the radial direction. And so the bit where it's going to be a bit hard to work out the electric field is inside this dielectric with permittivity epsilon. So the easiest way to work that out is with Gauss's law, but in this case, we want to use Gauss's law for the displacement. So we can write that the integral of the displacement over the surface, so we're taking a little Gaussian sphere like this, is equal to the enclosed free charge. And the enclosed free charge is just the total charge in here. There's no free charge inside the dielectric itself. It's not charged. So this enclosed free charge is just equal to Q. And we can write this part, because of the spherical symmetry, we can pull the dielectric out the front, and then that's going to be times the surface area of that sphere, which is 4 pi r squared. So this allows us to write that the displacement is equal to Q over 4 pi r squared. And then if we just think about directions, these are going to be parallel to each other. So this is going to be in the radial direction. So to make that a vector, we just need to add our little radial vector there. What we need is our electric field. So to get that, we can use our equation relating the permittivity and the displacement to the electric field, which is D is equal to the permittivity times the electric field. So this tells us that the electric field is equal to the permittivity divided by epsilon naught. So that's Q, not epsilon naught, sorry, epsilon, divided by 4 pi epsilon r squared times the radial vector like that. So this is in the region for A is less than R is less than B. This purple one is in the region for R is greater than B, and this red one is in the region R is less than A. Okay, so if we want to work out the total potential, we'll want to integrate the electric field over our entire path from infinity inwards here. So this is equal to minus the integral from infinity to B, and that's in the region where we've got 1 over 4 pi epsilon naught times Q over R squared, and this is dr. And then now we're inside the dielectric. So now we've got minus the integral from B to A. And now we need to use this equation for our electric field. So this is Q divided by 4 pi epsilon, sorry, not epsilon naught, that's automatic for me now, epsilon on R squared dr. And then we're inside our conductor where the electric field is 0. So this is going from A to 0 and it's 0 dr. Okay, so now what we need to do is do these integrals. With this one, we've got Q over 4 pi epsilon naught with our negative. When we integrate 1 on R squared, we get minus 1 on R, and that's from infinity to B. And with this next one, we've got minus Q over 4 pi epsilon. And then we also we're integrating 1 on R squared. And when we integrate that, again, we get minus 1 on R, and that's at B and A. And then this last part is just 0. So let's substitute, well, we can cancel out all our negatives, make everything positive here. And now we're going to want to substitute in our limits. So we've got Q over 4 pi epsilon naught. And here we've got 1 on B minus 1 on infinity. This is just 0. And then we've got plus Q over 4 pi epsilon. And here we've got 1 on A minus 1 on B. So this is equal to Q over 4 pi. We've got 1 on epsilon naught B plus 1 on epsilon A minus, oops, why did it jump around? Minus 1 over epsilon B. So that's an expression for the potential. So we've done the first part of this problem. We've come up with an expression for the potential. But now we need to find the polarization inside the dielectric. So we know that this is a linear dielectric. So this part is not too hard. We've got that P, just from the definition of a linear dielectric, is equal to epsilon naught times the susceptibility times the electric field. And as a step in this, we had to work out the electric field inside the dielectric. So it's just given by this. And so this is equal to Q epsilon naught times the susceptibility divided by 4 pi epsilon R squared R hat. So that's our polarization vector. Next, we need to work out the bound volume charge density. So to do that, we'll need to use that the bound volume charge density is negative the divergence of the polarization. So we've got the polarization here, so we just need to take the divergence of that. So because this only has an R component, we only need to worry about taking the derivative in the R direction. But remember, we are using spherical coordinates, so we do need to account for that. So that's going to be 1 on R squared times the derivative with respect to R of R squared times P. And P is this Q epsilon naught times the susceptibility over 4 pi epsilon naught. Oh, sorry, that's not epsilon naught, that's epsilon R squared. And these R squareds are going to cancel out. So what we're left with inside this derivative is a constant. So that is going to be equal to 0. So the bound charge density inside the dielectric is just equal to 0. And now to worry about the surface charge density. The surface charge density is given by the dot product between the polarization and the normal vector. And the normal vector is always out from the surface. So at B, the normal vector is directed out there. At A, the normal vector is directed in there like that. So we're going to get slightly different answers at our two surfaces. So at B, we'll have this is equal to PB. So here we'll have this R squared is equal to B, and the radial vector is out. This is an outwards radial vector, so those two are parallel to each other. And so this is just going to be equal to Q epsilon naught times the susceptibility over 4 pi epsilon B squared. And then at A, in this case, we've got the polarization is outwards while the normal vector is inwards. So this is going to have the opposite sign. So this is going to be equal to minus Q epsilon naught times the susceptibility divided by 4 pi epsilon A squared. Okay, so one thing to notice is that we have negative charge around here and positive charge around here. So this dielectric is slightly cancelling out the electric field in this region. So one way to think about dielectrics a bit is like a kind of weaker conductor. So if this was a conductor, we'd end up with all the charge on the surface of the conductor and it would perfectly cancel out this electric field. But in a dielectric, it's only partially cancelled out. Okay, now we're going to try a very challenging example, which is going to pull together a lot of the ideas from the different topics that we've learned so far. So in this example, suppose the entire region below the plane Z equals 0 is filled with a uniform linear dielectric material with a susceptibility, which is given by this chi subscript E. Calculate the force on a point charge Q situated a distance D above the origin. Okay, so let's start by drawing a diagram showing what's going on. We've got Z is equal to 0 here, and below that we've got our dielectric down here with some known susceptibility. And what we're considering is a point up above it here, a distance D above it with charge Q. And what we're asking is what's the force on this point charge here? Now, hopefully this reminds you a little bit of the questions that we were looking at when we were considering the method of images, where we were working out the force on a point charge due to a conducting sheet. Only now we don't have a conducting sheet. Now we've got this dielectric material instead. So we're going to apply a similar method to what we used when we had the conducting sheet, but we're going to have to account for this being a dielectric rather than a conductor. Okay, so when we were approaching it with the conductor, the first thing we did was work out what was the surface charge density. So we are going to do the same thing here. We want to find, but now it's our bound charge surface density. So we want to find sigma B. In order to do that, we can make use of this equation here for the polarization along with this equation, because we know that it's a linear dielectric material. So this relates the electric field to the polarization for a linear electric material. So we can write, well, sigma B is going to be equal to the polarization times the normal vector. And in this case, on this surface here, our normal vector is up out of the surface like that. So it's in the Z direction. So we're only considering the Z direction because that's the normal to our surface. So this is going to be equal to PZ, the polarization in the Z direction, which we can write as epsilon naught times the susceptibility times the electric field in the Z direction. So in order to work out what this is, we need to now find the electric field in the Z direction, and this is going to be due to two things. It's going to be due to our point charge Q, this charge here, and it's also going to be due to the charge distribution along this surface. So this surface charge distribution here, due to Q and sigma B. So let's work out what each of these is separately, and then we can add them together. Okay, so E in the Z direction due to Q. Let's consider a little point here, which is a distance R along here. So this is in the XY plane. If we were, if you were imagining like looking from on top, then there's a whole like circle of points which is going to satisfy this distance R away. So we are going to work out the electric field here as a function of R. And so this is just given by 1 over, oops, wrong color here. This is given by 1 over 4 pi epsilon naught. And then for electric fields, we multiply it by the charge, which is causing it, which is Q in this case. And then we are going to need this distance here, which if that's R and that's D, this is going to be the square root of R squared plus D squared. So that's over the distance squared, so that'll be R squared plus D squared, square root squared, so that gets rid of that. But it's now in the Z direction, so we just need that cos theta component there, because we only, this electric field here is going like this, and we just want this component here. And it's also, as I've drawn there, is going away from this positive charge. So it's going to be in the negative Z direction. So we need a negative to account for that. And we can write cos theta here as D over R squared plus D squared. So we can write this out as minus Q over 4 pi epsilon naught. And yeah, we'll replace the cos theta here with D over the square root of R squared plus D squared. That's what I'm doing in this next step. So this will be R squared plus D squared to the 3 over 2. And we've got a D on top. That's that D there. So this is the electric field at this point here due to this charge in the Z direction. But we'll also have an electric field here due to the dielectric. So E in the Z direction due to our dielectric, let's call it sigma B because it's due to those bound surface charges. Now, to work out what this is going to be, let's just find some space. I've put all this stuff here because we'll be referring to it later. But we're modeling this as having a bound surface charge here. Here's our point Q, and that's positive. So we're going to have a negative bound surface charge here. And we want to work out the electric field at this little point here. It's the same point as before. It's this point here. So I'm taking my Gaussian surface like that. I'm just drawing it on a fresh diagram so that it's a bit easier to see. Okay, now electric field lines point towards negative charges. So we can draw the electric field lines like this. I mean, obviously they've been over all the plate, but we're just considering this little Gaussian surface here. and my normal to my kind of prism is going to be away from the surface like this. And so I can say E dot dA, in this case, if I assume that the electric field is constant over these surfaces, then I can pull the electric field out the front, and so that's E. And then I've got two of these surfaces. I've got this surface with surface area A and this surface with surface area A. So that's going to be times 2A. And that is equal to the enclosed charge over epsilon naught. And the enclosed charge is going to be minus sigma B times A. Because it's a surface charge density, so all the enclosed charge is on here, and it's just that surface area times this surface charge density divided by epsilon naught. And so you can see when we're looking at this, this A is going to cancel that A. And so this tells me that the electric field is equal to minus sigma B over 2 epsilon naught. So that's my electric field due to these bound charges. Okay, so let's put this in here. This is going to be equal to minus sigma B over 2 epsilon naught. So now what I can do is I can get my total E in the Z direction, which is just going to be the sum of these two things. So this is going to be equal to minus QD over 4 pi epsilon naught R squared plus D squared to the 3 on 2 minus sigma B over 2 epsilon naught. And what we're trying to do is find this phi B. So what we'll do now is we'll replace this EZ here with phi B over epsilon naught times the susceptibility. So this is equal to phi B over epsilon naught times the susceptibility. Okay, now we're going to rearrange this equation to work out what phi B is. Let's simplify it a little bit. We can cancel out each of these epsilon naughts, and then we'll gather all the sigma B terms together. So we've got this is 1 over chi E plus 1/2, and that is equal to minus QD over 4 pi R squared plus D squared to the, that's a bit messy, to the 3 on 2. So just rearranging this a little bit, we can give it a common factor on the bottom. So this is sigma B. And if we put it over 2 times the susceptibility, then we've got 2 plus the susceptibility. And this 2 can then cancel with this 4 to become a 2. So hopefully you can now see that this gives us that the bound charge density is equal to the susceptibility divided by 2 plus the susceptibility. And we've got this negative here, so I'll put that there, times QD over 2 pi R squared plus D squared to the 3 on 2. Where, in this case, R squared equals X squared plus Y squared, because we were doing it in the, this is in the XY plane, and we said this was true for any points around that circle. So that circle is defined by this. Now, this is important because this is a good check, because we can see how the case for the bound charge compares with the case that we did before where we had the conductor. And you can see that these expressions are almost the same. We've got QD, negative, negative. We've got our 2 pi, R squared, D squared to the 3 on 2. So this suggests that these two are basically the same, but with, in this one we had the charge minus Q, and in this one the charge, the bound charge, is given by minus the susceptibility over 2 plus the susceptibility times Q. Now, we'd expect in the limit where our dielectric is behaving more and more like a conductor that these two things would agree, and the susceptibility goes to zero as you to infinity as you become more and more like a conductor. And you can see that as we send the susceptibility here off to infinity, we do indeed approach the result that we got over here. So far, so good. It's behaving as we would expect, but this was not what we were asked to find. What we were asked to find is the force. So in order to get the force, it's useful to know what the electric field is at this point here. So far we've been considering the electric field down here. So one way we could do that is to do the integral that the electric field is equal to 1 over 4 pi epsilon naught times the integral. This is just Coulomb's law, curly r hat over r squared times sigma b dA. But this is quite hard to do. So it turns out that it's actually easier to do it like we did over here with the method of images. But as always with the method of images, we need to be a little bit tricky about how we're going to do it, and especially so in this case. So in this case, what we actually need to match our potentials. So remember to apply the method of images. Okay, so to solve with the method of images, we need to find a charge distribution whose voltage and gradient of the voltage perfectly matches the situation that we're trying to set up. So in this case, it actually turns out to be a bit tricky. We need a different kind of charge setup to match the potential up here compared to down here. So let's, for above the plane, what we'll do is, this is our charge here, which is a distance d above. And with the methods of images charge, we take minus QB. Sorry, not minus QB, just plus QB down here. And this is a distance d below. And QB we found here. Okay, so to find the voltage at any point in the region above, we can write that the voltage, just using the law of superposition and considering both these charges separately, we've got 1 over 4 pi epsilon naught, and then we've got the charge, which is Q, divided by the distance. So that's x squared plus y squared plus z minus d squared. And then we've got the second charge, which is this one down here. So that is equal to QB divided by the square root of x squared plus y squared plus z plus d squared down here. So this is in the region for z is greater than 0. Now, in the region z is less than 0, we actually need to use a slightly different method of images. We take the charge Q plus QB at a height d above. And in that case, we can write that our voltage, let's call that plus and we'll call that minus. So this is the voltage down below here. So any point below here is given by 1 over 4 pi epsilon naught. And this is Q plus QB divided by the square root of x squared plus y squared plus z minus d squared. Okay, so let's show that this satisfies our requirements. We need our voltage. We've seen over here, we need our potential to be continuous. So if we put in Z equals 0, then we end up with this term's just D squared and this term's D squared. And so we've got Q plus QB all over X squared plus Y squared plus D squared, which is the same as this term over here. So it is continuous. So continuous. Okay, now it also needs to go to 0 at infinity. You can see all these terms are going to 0 at infinity. So limit at infinity is correct. And the other thing we need is, well, the gradient's not continuous, but we do need it to obey our condition, substituting this into here. The gradient of V above minus the gradient of V below has got to be equal to 1 over epsilon naught times sigma, which will be sigma B in this case. And this is normal, but let's just take these in the Z direction because we're only worrying about the Z direction. So yeah, this has to be the case. So what we need to do to check that is take the derivative of both of these things. So dV plus dz is equal to 1 over 4 pi epsilon naught. Then we've still got our Q. Now, this is x squared plus y squared plus z minus d to the minus a half, and we're taking the derivative of that. So when we take the derivative of something to the minus a half, we multiply it by minus a half, and then we have to times it by the derivative of what's in here, and we're doing it with respect to z. So when we take the derivative of this with respect to z, we get 2z minus 2d. So let's put that as 2z minus d. And then this is divided by x squared plus y squared plus z minus d square, to the squared to the 3 on 2. And then we've got our next term, which is our QB term, plus QB. And this ends up almost the same thing. We've got the minus a half and then 2, but now we've got the z plus d here. So this is z plus d divided by this. So this is x squared plus y squared plus z plus d squared to the 3 on 2. Okay, and the derivative of the other one, this one here with respect to z is 1 over 4 pi epsilon naught, and then we've got q plus qb times minus a half times 2 times z minus d over x squared plus y squared plus z minus d squared. Okay, and what we need is for these at the border here to be equal to, well, this should be minus sigma b in this case because this is a negative charge. So we'll need that equal to minus sigma b. So we need this evaluated at 0. Then we've got dv plus dz minus dv minus dz is equal to, these 2's and halves will cancel out everywhere, and we're substituting in z equals 0. So on the top here, the negatives will cancel out. We've got 1 over 4 pi epsilon naught in everything. And we've got q over x squared plus y squared plus d squared, because the z's 0 and this is to the 3 on 2. And then with this second term, we've only got the 1 negative sign here, whereas here we had the 2. So this ends up being minus QB. And that's that term with z equals 0 substituted in. So now what we need to do is substitute z equals 0 in here. Oh, and this should have been to the power of 3 on 2. Let's fix that up. That's 3 on 2. So now we substitute z equals 0 in here, and we're subtracting that off. So this is minus, so these two signs here will cancel each other out. So this is minus q plus qb divided by x squared plus y squared plus d squared, and this is to the 3 on 2. And I really am running out of space now, but hopefully you can see that these q terms are going to cancel out because we've got q and minus q, and we've got the same thing in the denominator, whereas here we have minus qb and here we have minus qb. And so this, where can I write it? Let's write it up here, is equal to minus 2qb divided by 4 pi epsilon naught, and then we've got x squared plus y squared plus d squared to the 3 on 2. So that 2 will cancel with that and leave a 2 pi epsilon naught. Okay, so we wanted this thing here to be equal to sigma b minus sigma b over epsilon naught. So here's sigma b, and if we replace this part here with QB, then this is equal to QBD divided by 2 pi r squared plus d squared to the 3 on 2. And r squared is just x squared plus y squared. I've dropped my d, but the d was there. I just forgot to write it down. I should have written that down. There is a d there. And this one here is divided by epsilon naught, which is this epsilon naught over here. But apart from that, they are the same. So the derivatives of the voltage meet Poisson's equation, and we get the expected results there as well. So that tells us that this setup for method of images, with taking it equivalent to this above, and if we're considering the force on the points below, considering this, so then I am totally out of space. But with methods of images, at this point it becomes easy to solve, because this is very easy to work out the force on Q4. So what this was asking me to calculate was calculate the force on the point charge Q situated a distance d above the origin, and now we're just working out the force with Coulomb's law this way. Okay, so we're just using Coulomb's law to write down that force. So the force is equal to 1 over 4 pi epsilon naught. The two charges, which is Q and QB, where QB is given by this relationship here. So we could substitute that in for that if we wanted to. And then divided by the distance, the separation squared, and they're separated here by a distance 2d. So this is divided by 4d squared. We will substitute in that QB just for the final step. So this is equal to minus 1 over 4 pi epsilon naught. That minus is this minus here times the susceptibility over 2 plus the susceptibility times Q squared over 4D squared. And it's a force in the Z direction. Okay, so hopefully you could follow that. This example's really made use of a lot of the stuff that we've been learning in this course. Right, now what we're going to do now is calculate the amount of energy we need in order to assemble a dielectric system. So let's start by picturing a parallel plate capacitor, as this is probably the kind of simplest dielectric system to imagine. So we've got our positive plate up here and we've got our negative plate down here. And there's an electric field inside the dielectric, which is smaller than the electric field would be without that dielectric, because the dielectric is polarized and the polarization cancels out some of the electric field. So we can write down that in this case, the electric field is equal to 1 over the relative permittivity, remembering the relative permittivity is equal to epsilon, which is epsilon naught times 1 plus the susceptibility divided by epsilon naught is what epsilon r is here. And so we can write that E is equal to 1 over the relative permittivity times the electric field that would exist if we had a vacuum. Now, remembering back to when we were considering capacitors, we said that the capacitance was equal to the charge on each of the plates. So one's got plus Q, one's got minus Q, divided by the voltage. And this voltage difference here comes about because of the electric field between the plates. So in this case, we've got a reduced electric field, and so we have a voltage which is reduced by the same proportion. So we'd have that the voltage difference between these plates with the dielectric in between them is equal to 1 over the relative permittivity of the voltage that would exist if we had a vacuum. And so this tells us, just substituting into here, for the same charge, if we've got the same charge on the plates as before, then we've got that the new capacitance is equal to epsilon r, the relative permittivity, times the capacitance that we'd have if we had just a vacuum between those plates. So we now have a higher capacitance. And now we can use this to calculate how much energy is stored in this capacitor, because when we were looking at capacitors, we calculated how much energy was needed to charge up our capacitor, and it's given by a half CV squared. So if we're charging it up to the same voltage V, then we'd have that the work needed to charge it to that voltage was given by a half epsilon r C vac V squared. So to get to the same voltage, we are going to need to do more work in this case, which makes sense because the field in here is cancelling out part of what we're doing, so we need to do more. So that's one way we can consider how much energy it takes to charge up this capacitor and make this arrangement. Another way we can do it is to follow a similar method to what we did back here when we were calculating the energy of a continuous charge distribution. It's just now we're calculating the energy which is needed when we've got this dielectric here. So back here we came up with the equation that the work that was needed to assemble a given charge distribution was equal to epsilon naught over 2 times the integral over all space of the electric field squared times d tau, the volume increment. Okay, so let's work through this for this case where we've got a dielectric. So in the case when we've got a dielectric, What we're worried about assembling is the free charges. The bound charges are going to look after themselves. The work that we need to do is to arrange the free charges how we want those arranged. So if we consider bringing in a little bit of free charge, then we can write down that the work that is needed to bring in this little increment of free charge is given by the free charge times the voltage times d tau. Now, we're considering free charges, and we know that Gauss's law for displacement, this is a D, tells us that the divergence of the displacement is equal to the free charge. So if now, rather than thinking about all the free charge, we're just thinking about a little increment of free charge, we can write Gauss's law for a little increment of free charge. So delta rho F, this little increment that we've got here, is going to just be a little increment of the displacement, so delta D. So what we can do is we can replace the little increment of free charge here with this expression here. So we will write this as the divergence of delta D times the voltage d tau. Okay, now what we're going to do is use this product rule number 5. Here we have the divergence of, this is a vector. Sorry, I didn't put my squiggle under there to show that this displacement is a vector. And this voltage here is a scalar. So in this case, this, okay, and we can just put brackets around there just to make this next step really clear. So next what we're going to do is we're going to use this product rule number 5, and here we've got the divergence of a vector times a scalar. So over here, this is the divergence of a vector times a scalar. That's the same as what we've got here, where F is V and delta D is RA. So we can use this to rearrange this and write this as the integral of the divergence of our scalar, which is V times our vector, delta D, minus our vector, which is delta D, dotted with the divergence of our scalar, which is delta V. And this is all times d tau. So that was just using this product rule on this line here. Now, what we're going to do on the next step is use our divergence theorem on that term here. And on this second term, we're going to remember what we saw at the very start, that the electric field is minus the gradient of the voltage. So we can write this as replacing this volume integral here with the surface integral. This is equal to V delta D dA. And then we've got a negative here and a negative here. So this is plus the integral of delta D dot E d tau. And we'll just put brackets around that to be very clear. And then what we can do is the same thing we did over here when we're considering this surface integral here. It's the surface integral over all space. So because it's getting so big, this is going to decrease rapidly with R a lot faster than this one increases. So it turns out that this entire thing here goes to 0, and we're left with just this term here. Okay, so in order to simplify that term, have a think about a half delta of d dot E. So this is like taking the partial derivative of this thing. Now, remembering from up here that the displacement is proportional to the electric field, and that proportionality is this permittivity, we can write this here as a half delta, and here we've got epsilon E dot E. And now what we'll do is we'll differentiate each of these in turn. So this is equal to a half, and we've got delta E, epsilon E dot E, plus a half epsilon E dot delta E. And with this term here, epsilon's just a constant. It's the permittivity, so we can move it out the front. And so both these terms are actually going to look the same. We're going to end up with, this is equal to a half epsilon delta E dot E plus a half epsilon E dot delta E, and it doesn't matter which order we do the dot product in, so this is equal to epsilon E dot delta E. But we can put our epsilon in front of our E, and so we can write this as delta epsilon E dot E, which from up here, this thing is just delta D. So this is equal to delta D dot E. Okay, and why we did this was that this is now this, so this lets us replace this with this. Okay, so we've got that work done on moving this little increment here of free charge into place in our dielectric is given by the integral of a half delta D dot E d tau, and we can, because everything else here is like this is just a constant, and we're just integrating, so we can move this delta out the front. So this is delta times a half the integral of d dot E d tau. And if we want to work it out for assembling this whole thing, this is how much work we needed to move one little increment. If we just sum up from 0, then we just get rid of this delta. So this tells us that W is equal to a half the integral of d dot E d tau. Okay, so this equation tells us how much energy we need to apply to assemble a certain like charge distribution with electric field E and displacement D when a dielectric is present. Now you might be thinking, well, why couldn't we just use this one and just consider placing all those free and bound charges? And in fact, if we did that, we'd end up with a different number, because this would be E dot E still, and here we've got D dot E. So what's going on there? Why aren't these two the same thing? But this one here is calculating the work done as we assemble these charges to form this dielectric. So we haven't actually considered in this case placing those bound charges. Those bound charges have rearranged themselves because of the electric field. So they're like generating their own polarization. If we were to use this equation, we would need to consider placing all the free and all the bound charges. And so with this one, we would end up with a larger number. except that the reality is that the system rearranges the bound charges itself. So if we were to actually physically assemble this, we would not need to do that work. The system would do that work for us. Now this one's a little bit fun. We're going to now consider the forces on the dielectrics. So really we'll be considering how much force is required to pull a dielectric out of a capacitor like this. So what's this applied force here in order to get this dielectric out of these capacitor plates here? Okay, so in order to do this, the amount of work that we need to do in order to pull it out can be calculated with dW is equal to the applied force times dx when this applied force is parallel to the x direction. So that's measuring how far it has come out of the space between these plates. Now, the electric field is going to be applying a force which opposes this applied force. That's what we're doing the work against. That's why it's hard to pull it out, because the electric field has a force in the other direction. So we will have that dW is equal to minus F dx, where this F is due to electric field. Now, this would be hard to calculate directly because this electric field is a little bit complicated. Between the plates, it's just a straight vertical field, so that would be easy. But we've got like a fringing field, like it loops around out the outside here, and it's a little bit complicated. So this would be fairly hard to calculate directly. But luckily, there's a little bit of a kind of trick that we can use. We know how much energy is stored in the capacitor. We've calculated it before, and I've written it down here. The energy stored in the capacitor is given by a half CV squared. And if we think about the capacitance for this setup here, where we've got this dielectric, which is a distance x from this end of a capacitor plate. Hopefully you remember from physics 1b that the capacitance of a parallel plate capacitor is given by A epsilon naught over D, where A is the area of the capacitor plate. So in this case, that would be L times W. Now, what makes this a little bit complicated is that part of this doesn't have the dielectric in it, and part of this does have the dielectric in it. So we can really consider it as being two capacitors in parallel. There's this part which doesn't have the dielectric, and then there's this part which does have the dielectric. Okay, so in this case, let's start by considering the bit that doesn't have the dielectric. The capacitance for that is equal to, well, we've got epsilon naught over D, and then it's multiplied by the area. So it's got a width, W, and the area of this part here is just equal to X. And then we've got this part here, which does have the dielectric. So this one here has a length given by L minus X, and it has a relative permittivity of epsilon R. So we can write this as epsilon naught W over D. And here we've got X plus L epsilon R minus X epsilon R. And this is equal to epsilon naught W on D. And then we've got X outside of 1 minus epsilon R plus L epsilon R. Righto, and then for this part, remembering when we were looking at polarization and we got these relationships up here, you can see here that 1 minus the relative permittivity is going to be the negative of the susceptibility. So this thing here is going to be equal to negative of the susceptibility. So we can write this as epsilon naught W over D. And let's just switch the order of these terms. We've got L times the relative permittivity minus the susceptibility times X. So we've now got an expression for the capacitance in this case. But what we're looking for is the force. So let's go back to this equation and rearrange it. So we've got the force is equal to minus dW dx, and this is the force applied by the electric field. Now, what we're going to need to do is think carefully about the situation. Because we're dealing with works here, we want the only work to be due to the electric field, which is like equal and opposite to this applied force. So for that to be the case, we can't have any other active components there. So we can't have it connected to a power supply. If we were using this equation here to calculate the work done, this would kind of imply that we were charging it up as we go, because we're considering the voltage there. So what we're going to do instead physically is this plate is going to have a charge plus Q. This plate is going to have a charge minus Q, and those Qs are set before we start pulling this slab out. So we've set the Qs, it's not attached to a battery, now we're pulling it out. So in this case, combining these two equations, because we've now got Q fixed and our capacitance is given by this expression here. So we can write, we're replacing this V squared here with Q squared on C squared. So we can say that this is equal to a half Q squared on C. Okay, so that's our expression for work. And now what we can do with this force is use our product rule. We can write this as minus dW dC times dC dx. And now these are all things that we can find because we've got W in terms of C here. So we just need to differentiate this. So this is a half Q squared C to the minus 1. And when we differentiate, we get a half, minus a half Q squared over, and this is C to the minus 2, so over C squared. And then we have to differentiate this term with respect to X. So that gives us the epsilon naught W on D, and then we've got the negative of the susceptibility. Okay, so in this we've got three negative signs. So we've got one of those left, and Q squared on C squared, that's just going to be the voltage squared to whatever it was set to. So this is a half epsilon naught W susceptibility divided by D and then times V squared. So I'm replacing the Q squared on C squared with the V squared. And so we've now derived how much force we'd need to apply in, this equation here gives us the force applied by the electric field, which is in the opposite direction to the force that we would need to apply to pull it out.